Right now, without any sensation at all, something is passing through the chair you are sitting in, through the floor beneath it, and through your own body, at about 220 kilometers per second, roughly a third of a proton's worth in every cubic centimeter. It has been doing this every second of your life, and no instrument ever built has registered it doing anything whatsoever, except bending the paths of stars. But here is what that description quietly assumes. Every mass ever measured beyond the Earth was weighed the same way. Measure a motion, assume a law, solve for the mass. 93 years ago, that method started returning answers 5 times too large, and it has never stopped. And when physicists finally studied the shortfall itself, instead of hunting for whatever causes it, they found something nobody expected. It has a shape, a single acceleration threshold, identical in every galaxy ever measured, whose value happens to match the expansion rate of the entire universe. So which is actually missing, the matter or the law? By the end of tonight, you will know exactly why nobody can say yet, and why whoever finally does will not have answered one question. Settle in, hit subscribe if you're new here, because by the end of this, the number on the scale will never mean quite the same thing again. Now, let's slowly ease into this. Part 1. The only scale we have. Nobody has ever weighed a star. That sentence sounds like a trick, and it is not. There is no scale large enough, no balance, no lever, no way to set the sun on one side of anything and pile up known masses on the other until the two agree. And yet, if you look up the mass of the sun tonight, you will find it stated to remarkable precision, about 1.989 times 10 to the 30th kilograms, 2,000 billion tons, give or take a rounding error that would swallow the Earth several thousand times over. So where does that number come from, if nobody has ever weighed it? It comes from watching us move. The Earth travels around the Sun at about 30 kilometers every second, on a path with an average radius of roughly 150 million kilometers, and it completes one full circuit in a year. Those 3 facts, plus one equation, give you the mass of the Sun. The equation is Newton's, published in 1687, and it says that the gravitational pull between two objects depends on their masses and on the square of the distance between them. Rearrange it. If you know how fast something is going around, and how far out it is, you can solve for how much mass must be sitting at the center holding it in that curve. That is the whole method. It is not one technique among several. It is the method, and it is used everywhere. The mass of Jupiter comes from watching its moons. Galileo saw 4 of them through a small telescope in 1610, and once you know how long Io takes to go around and how far out it sits, Jupiter's mass falls out of the same equation. The mass of a distant star comes from watching its binary companion swing around it. The mass of a galaxy comes from watching its outer stars circle the center. The mass of a cluster of galaxies comes from watching how fast the individual galaxies inside it are moving relative to one another, and asking how much gravity would be needed to keep them from flying apart. In every single case, the procedure is identical, and it is worth saying it slowly, because the rest of tonight lives inside it. You measure a motion, you assume a law, you solve for the mass. Measure a motion, assume a law, solve for the mass. 3 steps. The first step is observation, and it is the part we are extremely good at. Spectroscopy can tell you how fast an object is moving toward or away from you by looking at how its light is shifted. And modern instruments do this to a precision of meters per second on stars hundreds of light years away. The third step is arithmetic. It is the middle step, quietly sitting there between the two, that nobody thinks about. Because we cannot check the middle step independently. Not out there. We can check Newton's law in a laboratory, and we have. exhaustively. We can check it in the solar system, and we have, to the point where spacecraft navigation is a solved engineering problem. But the moment you apply it to a galaxy, you are extrapolating a law that was calibrated on falling apples and orbiting planets out to distances 100 billion times larger, and to accelerations trillions of times gentler, and there is no way to verify the extrapolation except by assuming it and seeing whether the answer looks sensible. For a long time, the answers did look sensible, and then they stopped, beginning in the 1930s, and with real force from the 1970s onward. That three-step procedure started returning masses that did not match anything anyone could see. Not slightly, galaxies came back weighing 5 to 10 times more than the sum of everything shining inside them. Clusters of galaxies came back weighing hundreds of times more than the light suggested. And when the same accounting was finally done for the universe as a whole, the result was that everything that emits, absorbs, reflects, or scatters light, every star, every cloud of gas, every planet, every grain of dust, every person, adds up to about 4.9% of the total. The matter inferred purely from gravity comes to about 26.5%. The ratio between them is 5.36 to 1. There are exactly two ways to read a result like that, and it is important to be clear-eyed about both. The first reading is that the universe contains a great deal of matter that does not interact with light. It has mass, it has gravity, and it is otherwise invisible in a way no substance in your experience is invisible, not transparent, like glass, which bends light and reflects a little, not clear, like air, which scatters blue, genuinely, completely uncoupled from the electromagnetic force, so that photons pass through it as though it were not there, because as far as photons are concerned, it is not. The second reading is that there is nothing missing at all, and the middle step is wrong. The law we assume when we convert motion into mass is simply not the correct law in the regime where we are applying it. Newton's inverse square gravity is a superb description of the solar system and a poor description of a galaxy's outskirts, in the same way that Newton's mechanics is a superb description of a train and a poor description of a particle accelerator. In that reading, the missing mass is an artifact, a shadow cast by using the wrong equation. 93 years after the first person wrote the discrepancy down, physics has not established which of those two readings is correct. That is not the interesting part. The interesting part is what happened in the meantime, because while the argument about what the discrepancy means has gone in circles, the measurement of the discrepancy itself has become extraordinarily precise. We have mapped it galaxy by galaxy, cluster by cluster, and across the whole observable sky. We have measured where it is, how much of it there is, how it is distributed, and how it behaves. And somewhere in that mapping, something turned up that almost nobody outside the field talks about, and that changes the entire character of the problem. The shortfall has a shape. It is not scattered. It is not random from galaxy to galaxy. It does not vary with size, or mass, or age, or brightness in the way you would expect if it were simply a matter of how much invisible material happened to collect around each object. It switches on at one specific, universal threshold, the same threshold in every galaxy ever measured. And once it switches on, the visible matter, the 4.9%, the part we can actually see, predicts the invisible part so precisely that you can draw one from the other, point by point, with almost no scatter at all. That regularity is the reason this problem has stopped behaving like a gap in our knowledge, and started behaving like a keystone. And it is why the claim in tonight's title is not hyperbole, but we are nowhere near ready to say why. First, we have to understand exactly how solid the discrepancy is, and that means going back to a short section at the end of a review paper written in Switzerland in 1933 by a man almost nobody could stand. Part 2. The first time the scale broke. Fritz Zwicky was Swiss-Bulgarian, worked at Caltech, and had a reputation for calling colleagues he disagreed with spherical bastards, on the grounds that they were bastards whichever way you looked at them. He also predicted neutron stars, predicted supernovae as a distinct class of object, predicted gravitational lensing decades before anyone observed it, and compiled catalogues of galaxy clusters that are still in use. He was right about an unusual number of things and pleasant about almost none of them, and the combination cost him. In 1933, he published a paper in a Swiss journal, Helvetica Physica Acta, Volume 6, titled The Redshift of Extragalactic Nebulae. It is mostly a review of ideas about redshift. The part that mattered is section 5, near the back, under the heading Comments on the Velocity Dispersion in the Coma Cluster of Nebulae. It runs a few pages. It is, by a wide margin, the most consequential thing in the paper, and it reads like an afterthought. Here is what he did. The Coma Cluster is a swarm of galaxies, about 320 million light-years away, in the direction of the constellation Coma Berenices. Zwicky had spectra for 8 of its member galaxies, which does not sound like many, and was in fact a considerable achievement, because photographic plates in that era needed exposures of up to 50 hours and more per object. 50 hours of a telescope's life, spread over many nights, to get one number. The 8 numbers he got were these: 8,500 kilometers per second, 7,900, 7,600, 7,000, 6,000, 6,700, 6,600, and 5,100. He flagged the last as possibly not a cluster member at all, and put the odds of that at about 1 in 16. What he cared about was not the average of those numbers. It was the spread. The galaxies were not all moving together. They were moving relative to one another by, in his words, at least 1,500 to 2,000 kilometers per second. Now apply the method. Measure a motion, assume a law, solve for the mass. Zwicky used a piece of classical mechanics called the virial theorem, which relates how fast the members of a bound, settled system move to how much mass is holding them together. If galaxies are flying around inside the cluster at those speeds, and the cluster is not visibly coming apart, gravity must be strong enough to keep them. So how much mass does that require? He put in the numbers he had. A cluster radius of about 1 million light-years, roughly 800 galaxies, each galaxy weighing about 1 billion times the Sun, which was Edwin Hubble's estimate at the time. And he got a mismatch. Not a small one. In his own words, in order to obtain, as observed, a medium-sized Doppler effect of 1,000 kilometers per second or more, the average density in the Coma system would have to be at least 400 times greater than that derived on the basis of observations of luminous matter. 400 times. Then he wrote the sentence. If this should be verified, it would lead to the surprising result that dark matter exists in much greater density than luminous matter. In the original German, dunkle Materie, dark matter, with the Swiss spelling of the comparative, größere, which is how you can tell the paper was set in Zurich. He was not being careless. In the same short section he considered and dismissed the obvious escape routes, one by one. Perhaps the cluster is not settled, not in equilibrium, so the virial theorem does not apply. He calculated that this buys you a factor of 2 at most. Perhaps the cluster is simply flying apart, unbound, and we are watching the debris. He rejected that, because the spread of speeds among galaxies outside clusters does not exceed 200 kilometers per second. So where would this population have come from? Perhaps the redshifts are gravitational rather than kinematic, light climbing out of a deep well. He ran that number, and it corresponds to a speed of 10 meters per second, 7 orders of magnitude too small. He also, and this is important, got the arithmetic wrong. Zwicky's calculation depended on the Hubble constant. the number relating a galaxy's distance to its recession speed, and in 1933, the accepted value was about 558 kilometers per second per megaparsec. The modern value is about 67. Zwicky's figure was too large by a factor of roughly 8.3, and that error propagates straight into his mass estimate. His 1937 follow-up, published in English in the Astrophysical Journal, gave a mass-to-light ratio of about 500 in solar units. Divide by 8.3 and you get about 60. 60 is still wrong. Not wrong in the sense of being an error, wrong in the sense of being impossible. A population of ordinary stars produces a mass-to-light ratio of a few. 60 means that for every unit of light you see, there are roughly 20 times more mass present than any stellar population can account for. The modern measurement of coma sits somewhere between 200 and 400. So Zwicky's arithmetic was off by nearly an order of magnitude, and his conclusion survived the correction completely intact. That is a rare thing in the history of science, and it should have been taken seriously. It was not. 3 years later, in 1936, an astronomer named Sinclair Smith did the same exercise on the Virgo cluster and found the same problem. A total mass of about 100 trillion suns spread over 500 galaxies, which works out to 200 billion solar masses per galaxy, against Hubble's estimate of 1 billion. 200 times too much. Hubble himself cited Smith in his book The Realm of the Nebulae, and called the discrepancy real and important. He did not cite Zwicky. In 1940, an astronomer named Erich Holmberg wrote what may be the most honest sentence of the entire period. It does not seem to be possible, he said, to accept the high velocities, unless we suppose that a great amount of mass, the greater part of the total mass of the cluster, is contributed by dark material distributed among the cluster members. And then he added 4 words. An unlikely assumption. That was the state of the field. The measurement was accepted, the implication was refused, not because anyone had found a flaw, but because the implication was intolerable. In 1954, Martin Schwarzschild, one of the most careful stellar astrophysicists of the century, reanalyzed coma with better data. He got a velocity dispersion of 630 kilometers per second and a mass-to-light ratio of 800, which he described, in print, as bewilderingly high. That is the vocabulary of a man who has checked his work and does not like what it says. By 1961, there was a conference in Santa Barbara devoted to the problem, and the summary, written by 3 statisticians and astronomers afterward, reads, "Many of those present consider that it might be real, and due to invisible intergalactic material in the clusters, totaling 90 to 99% of their mass." 28 years after Zwicky, the community had traveled the distance from dismissal to unease, and stopped there. What broke the deadlock was not a better cluster measurement. It was a completely different kind of object, measured by somebody who was not looking for missing mass at all, and who found it in a place where there was no way to argue about equilibrium or membership or whether the system was settled, because the system in question was a single galaxy, quietly turning. Part 3. The curve that would not fall. Consider the solar system for a moment, because it is the cleanest example of gravity behaving exactly as it should. Mercury orbits the Sun at about 47 kilometers per second. Earth, further out, moves at 30. Jupiter, further still, at 13. Neptune, right out at the edge, crawls along at 5.4. The pattern is not an accident, and it is not a coincidence of formation. It is a direct consequence of where the mass is. Almost all of the solar system's mass, better than 99.8% of it, sits in the Sun, at the center. Once you are outside that concentration, the pull weakens with the square of your distance, and orbital speed falls off as 1 over the square root of the radius. That relationship has a name. It is called a Keplerian fall-off, and it has a very simple signature. Double your distance from the center, and your orbital speed drops by about 30%. Every time. It is one of the most reliable curves in physics. Now hold that shape in mind and point it at a galaxy. A spiral galaxy looks, from the outside, like a solar system scaled up. There is a bright, dense concentration at the middle, where the stars are packed close and the light is intense. There is a disk around it that thins out with distance until the stars run out entirely and the darkness takes over. If the mass follows the light, and there is no obvious reason it should not, since stars are what galaxies are made of, then the outer stars should behave exactly like Neptune. They should be moving slowly, and the further out you look, the slower they should be going. In 1970, an astronomer named Vera Rubin and an instrument builder named Kent Ford published a paper in the Astrophysical Journal called Rotation of the Andromeda Nebula from a spectroscopic survey of emission regions. They had measured 67 bright clouds of ionized hydrogen scattered through the Andromeda Galaxy, our nearest large neighbor, at distances from 3 to 24 kiloparsecs out from the center. They measured how fast each of those clouds was moving, and they plotted speed against distance. The line did not fall. It went out from the bright core, and it rose, and then it flattened, and then it just kept going, flat. At the last measured object, 24 kiloparsecs out, well beyond the point where the visible galaxy had faded into nothing much, the stars and gas clouds were still moving at essentially the same speed as material far closer in. The integrated mass of the galaxy, they wrote, continued to increase out to the last measured object. Think about what a flat line means in the frame we have just set up. It means that as you move outward and the light disappears, mass keeps being added. Not a little, enough to exactly compensate for the increasing distance so that the speed never drops. Somewhere out past the visible edge of Andromeda, there is more material, and then more, and then more, arranged in such a way that the rotation curve refuses to bend. Spiral galaxies plateau at speeds of roughly 100 to 300 kilometers per second, with the big bright ones clustering around 200 to 250. Andromeda's outer curve sits near 230 to 260. Our own galaxy does something very similar. The Sun is moving around the galactic center at about 230 kilometers per second, roughly 828,000 kilometers per hour, from a distance of about 8.2 kiloparsecs, which is 26,700 light-years, a figure now pinned down by 16 years of tracking a single star called S2 as it whips around the black hole at the center. I want to pause on the instrument, because this is one of those cases where the tool determines what can be known. The reason nobody had done this measurement properly before was that the outer regions of a galaxy are extremely faint. To get a spectrum of a gas cloud at the edge of Andromeda with the photographic technology of the 1950s would have taken an absurd amount of telescope time, the same problem that gave Zwicky 8 galaxies instead of 800. Kent Ford, working at the Carnegie Department of Terrestrial Magnetism, built an image tube spectrograph. The principle is straightforward. Put a photocathode in front of the plate, so incoming photons knock electrons loose. Accelerate those electrons onto a phosphor screen. The picture that comes out the other side is many times brighter than the one that went in. Exposure times dropped by roughly a factor of 10. That is what made the faint outskirts observable at all. And the faint outskirts are exactly where the anomaly lives. The instrument that opened this problem was built to solve a completely different practical annoyance, and it happened to point straight at the one place in a galaxy where the books do not balance. Rubin and Ford did not stop at Andromeda. In 1978, with Norbert Thonard, they published rotation curves for 10 high-luminosity spirals, all flat out to the outermost measured radius. In 1980, they published 21 more, in a paper whose title tells you the whole story: Rotational Properties of 21 SEC Galaxies with a Large Range of Luminosities and Radii, from NGC 4605 at 4 kiloparsecs to UGC 2885 at 122 kiloparsecs. A factor of 30 in size. Same answer every time. Eventually they worked through some 60 spiral galaxies, and every one of them did the same thing. And, characteristically, Rubin spent a good deal of effort making sure other people got credit. Radio astronomers had been seeing hints of this for years using the 21-centimeter line of neutral hydrogen, which extends further out than the visible gas clouds do. Morton Roberts had measured Andromeda that way in 1966. Albert Bosmer's 1978 doctoral thesis presented velocity fields for 25 galaxies and reached further out than the optical work, and appeared a few months before the Rubin and Ford paper of the same year. In their own paper, Rubin, Ford and Thonard wrote plainly, Roberts and his collaborators deserve credit for first calling attention to flat rotation curves. Nor was she the first person to notice the shape. Horace Babcock's 1939 doctoral dissertation measured Andromeda out to 100 arc minutes and found an outer curve that would not fall, and wrote, with real care, because his data were partly wrong, and he seems to have suspected it, that the result suggests either that absorption plays a very important role in the outer portion of the spiral, or, perhaps, that new dynamical considerations are required. That is the whole modern debate, written in 1939, in a sentence with the word "or" in the middle of it. In 1970, in an appendix to a paper about something else entirely, Ken Freeman looked at two galaxies and wrote, there must be in these galaxies additional matter which is undetected, either optically or at 21 centimeters. Its mass must be at least as large as the mass of the detected galaxy. And in 1973, there arrived a piece of evidence from a completely different direction, theory rather than observation. Jeremiah Oestreicher and Jim Peebles ran computer simulations of flattened, rotating galaxies with a few hundred mass points and asked a simple question, which they put in their title: Can cold galaxies survive? The answer was no. Disks like the Milky Ways turned out to be, in their words, rapidly and grossly unstable to bar-like modes. Left to themselves, they buckle and collapse into a bar within a few rotations. What stabilizes them is a spherical halo of extra mass, 1 to 2.5 times the mass of the disk. So by the mid-70s, invisible mass was needed not only to explain how fast galaxies spin, but to explain why spiral galaxies still look like spirals. Two independent papers in 1974, one by Oestreicher, Peebles and Yahil, and one by Einasto, Karsick and Saar, both opened by stating that galaxy masses had been underestimated by about a factor of 10. By 1979, Sandra Faber and Jay Gallagher were writing in a review that the case for invisible mass in the universe is very strong and becoming stronger. Rubin's own account of how the field turned is characteristically dry. Many people, she told an interviewer in 1989, initially wished that you didn't need dark matter. It was not a concept that people embraced enthusiastically, but the observations were undeniable enough so that most people just unenthusiastically adopted it. Asked how she had convinced the skeptics, she said, all you had to do was show them a picture of the spectrum. She had been told, when she applied to graduate school, that Princeton does not accept women. The astronomy program there did not admit any until 1975. She was the only astronomy major in her class at Vassar in 1948. She took her doctorate under George Gamow. She received the National Medal of Science in 1993 and the Gold Medal of the Royal Astronomical Society in 1996, the first woman to be given it since Caroline Herschel in 1828, a gap of 168 years. She died on Christmas Day, 2016, at the age of 88, without a Nobel Prize, and since the Nobel is not awarded posthumously, she will not receive one. Her line about all of this was that In a spiral galaxy, the ratio of dark to light matter is about a factor of 10, and that this is probably a good number for the ratio of our ignorance to our knowledge. "We are out of kindergarten," she said, "but only in about 3rd grade. Hold on to that, because we will come back to it at the end, and it will mean something different by then. But a flat rotation curve, on its own, is still just one measurement made one way. It rests on assumptions that the orbits are circular, that the disk is in a steady state, that we are reading the geometry correctly. If the whole case for missing gravity rested on rotation curves, there would be a genuine argument to have. It does not. And that is the part that closes the door." Part 4. 6 Witnesses Who Never Met. The single most common misunderstanding about this problem is that it rests on rotation curves. It does not. It rests on 6 separate measurements, and the important thing about them is not that they agree, it is that they have almost nothing in common. They use different instruments, they probe different objects. They sample different epochs of cosmic history, separated by billions of years. They make different assumptions, and crucially, they fail in different ways. If you wanted to invent a single mistake that would produce all 6 results, you would find that no such mistake exists, because a flaw that corrupts one of them leaves the others untouched. Let me take them one at a time. The first witness is galaxy rotation, which we have just met. It assumes Newtonian dynamics and roughly circular orbits, and it returns 5 to 10 times more mass than the light accounts for, in essentially every spiral galaxy ever measured. Its weak point is the assumptions about the orbits and the geometry of the disk. The second witness is cluster dynamics, which is Zwicky's method, and it has nothing in common with the first. There is no rotation involved. Galaxies in a cluster move on wildly different paths in every direction. It also has a second, independent form. Instead of tracking individual galaxies, you can measure the temperature of the hot gas that fills the cluster and glows in X-rays. Hotter gas means faster moving particles, which means a deeper gravitational well is required to keep the gas from evaporating away. 2 completely different measurements of the same object, one using galaxies as test particles and one using the thermal state of a plasma. Both give dark to ordinary ratios of around 5 to 6 to 1. The third witness is gravitational lensing, and this is the one that changes the epistemic situation entirely, so it is worth slowing down. General relativity says that mass curves spacetime and that light follows the curvature, so a concentration of mass in front of a distant galaxy will bend that galaxy's light as it passes, distorting its apparent shape. In the strong case, this produces multiple images, or arcs, or a complete ring. In the far more common weak case, it produces a distortion of about 1%, far too small to notice in any individual galaxy, but detectable statistically across hundreds of thousands of background galaxies whose shapes are all being stretched in a coherent pattern by the same intervening mass. Here is what makes it different from everything else. Weak lensing measures the projected mass directly. It does not assume the system is settled. It does not assume anything is orbiting. It does not assume that light traces mass. In fact, it does not care about the light at the lens at all. It weighs the mass without requiring the mass to shine. That means every objection you might raise about equilibrium, or about hidden motions, or about whether a cluster is properly bound, simply does not apply. And the answer lensing gives is the same answer. The Dark Energy Survey mapped roughly 4,000 square degrees of sky from the shapes of over 100 million galaxies. A more recent combination covers 13,000 square degrees from 270 million. The clustering strength those maps return agrees with the value derived from the microwave background to within a few %, and the 2 measurements share no methodology whatsoever. The fourth witness is one specific object, and it is the closest thing this field has to a photograph of the problem. It is a system catalogued as 1E 0657-558 at a redshift of about 0.3, some 3.7 billion light-years away. Two galaxy clusters have collided and passed through one another. In 2006, a team led by Douglas Clow published a paper with a title that does not hedge, a direct empirical proof of the existence of dark matter. What makes a collision useful is that different kinds of matter behave differently in one. The galaxies themselves are effectively collisionless. They are tiny compared to the distances between them, so two clusters can pass through each other, and almost no galaxy will strike another. They sailed through. The hot X-ray gas, which is where roughly 90% of the ordinary matter in a cluster actually lives, is a fluid. Fluids collide. It piled up, shocked, heated, and was left behind in the middle, dragging. So after the collision you have ordinary matter, mostly in one place, the gas, stranded in the center, and galaxies out ahead of it on either side. Then they mapped the gravity, using lensing, which requires no assumption about the force law at all. And the gravity was not with the gas, it was out ahead, tracking the galaxies. The offset between where the mass is and where the ordinary matter is measures out at 8 sigma. In an ordinary settled cluster, the invisible mass and the visible gas sit on top of one another, and you can always argue about modeling. This collision pried them apart, and the gravity went with the invisible component. The fifth witness comes from a time before any galaxy existed at all. 380,000 years after the beginning, the universe cooled enough for electrons and nuclei to combine into neutral atoms, and light, which until then had been trapped, scattering endlessly off free electrons, was released. That light is still arriving. We call it the cosmic microwave background, and it is the oldest thing anyone can see. It is not perfectly smooth. There are temperature variations across it at the level of about 1 part in 100,000, and the statistical pattern of those variations encodes the contents of the early universe with astonishing precision. The final results from the Planck satellite give the ordinary matter density, the cold dark matter density, the dark energy fraction, the expansion rate, and the age of the universe, 13.797 billion years, plus or minus 23 million. The characteristic angular scale in that pattern is measured to 0.03%, which makes it one of the most precise measurements in all of science. And that pattern says, unambiguously, that most of the matter present at 380,000 years was not made of atoms. We will get to exactly how it says that in a moment, because the argument is beautiful and almost nobody explains it properly. The sixth witness is not a measurement at all. It is an accounting problem about time. The ripples in that early light are 1 part in 100,000. Gravity amplifies ripples. Dense regions pull in more material and become denser. But in an expanding universe, the amplification is slow. Density contrasts grow in proportion to the scale factor, which is to say, in proportion to how much the universe has expanded. Since that light was released, the universe has expanded by a factor of about 1100. So take 1 part in 100,000, multiply by 1100, and you get about 1 part in 100. To collapse into a bound object, a galaxy, a star, anything, a region needs a density contrast of about 1. Not 1%, 1. A universe made only of ordinary matter, starting from the ripples we can actually see in the microwave background, would today be a smooth, featureless fog. It would be 100 times short. There would be no galaxies, no stars, no planets, and nobody to notice. We observe galaxies that had already formed when the universe was less than 500 million years old. 6 witnesses, different instruments, different objects, different epochs, different assumptions, different failure modes. All of them off in the same direction, and all of them off by the same amount. You are not being asked to trust one measurement. You are being asked either to accept that conclusion or to find a single mistake capable of producing all six, and no one, in 93 years, has proposed one. Which leaves the sixth witness sitting there with a question attached. If ordinary matter could not have built anything in the time available, how did anything get built? The answer to that involves a head start, and the size of the head start is where this stops being an abstraction and starts being about you. Part 5. The head start. Put yourself somewhere in the universe, about 100,000 years after it began. There is no darkness here. There is no such thing. You are inside a plasma, so dense and so bright that light cannot travel any meaningful distance before it strikes a free electron and is thrown off in a new direction. There is no seeing. There is only glow, in every direction, uniform, at a temperature of several thousand degrees. If you could somehow be present, you would not be able to make out your own hand, not because it is dark, but because the light arriving at your eye carries no information about where it came from. It has been scattered too many times. Now feel the mechanics of this place. Matter here, protons, helium nuclei, electrons, is bound to that light. Not metaphorically bound, physically coupled, because charged particles scatter photons, and photons push. Matter and radiation are one substance, a single fluid with enormous pressure. Somewhere nearby, a region is slightly denser than average. 1 part in 100,000 denser. Gravity begins to pull material toward it, and as the fluid falls inward, it compresses, and compressing it, raises the radiation pressure, and the pressure pushes back out, so the region does not collapse. It overshoots, expands, overshoots again, and falls back. It rings. Across the whole universe, on scales of hundreds of thousands of light years, the fluid is ringing, standing waves of compression and rarefaction, in and out, for hundreds of thousands of years. It is the largest sound anyone will ever be unable to hear, and while it rings, it does not grow. Every attempt to build structure is answered and cancelled. Now shift your attention to what is not ringing. Threaded through the same volume, occupying the same space, there is something that does not feel the light at all. Photons pass through it as though it were not present. It has no pressure to push back with, because pressure requires interaction, and it does not interact. So when gravity pulls it inward, nothing stops it. It simply falls, quietly, steadily, without oscillating, for the entire duration. And where it gathers, the geometry deepens, real gravitational wells, growing steadily deeper, while the ordinary matter beside them is still trapped in its sound wave, going nowhere. Then, at about 380,000 years, the temperature drops through about 3,000 Kelvin, and electrons and nuclei combine into neutral atoms. Over a few tens of thousands of years, the fog clears. The light, suddenly with nothing to scatter off, goes free in every direction at once, and begins the journey that ends in a radio telescope 13.8 billion years later. And the ordinary matter, released, finds the landscape already carved. The change is not gradual. The moment the coupling breaks, the speed of sound in the matter drops by about 5 orders of magnitude, and the minimum mass that can collapse under its own gravity drops by around 14. Everything that was forbidden a moment ago is now compulsory. The gas, which had built up density contrasts of only 1 part in 100,000, falls into wells that are already far deeper than that, and within a few expansion times, it catches up completely. That is the head start. About 380,000 years of a substance that ignores light quietly building the framework, while everything you are made of was stuck in a standing wave. This is where the problem stops being an accounting curiosity about distant galaxies and becomes personal, so I want to state it plainly. You exist because of the head start, not in a poetic sense, in a strictly arithmetic one. Take the ripples we can directly see in the microwave background. Apply 13.8 billion years of gravitational growth in an expanding universe, and you do not get galaxies. You get a smooth fog with variations of about 1%, 100 times too weak to have collapsed into anything. Every structure in the universe, every galaxy, every star, every planet, every atom in your body that was forged in a stellar core is downstream of the fact that something invisible started gathering 400,000 years before ordinary matter was allowed to. The missing gravity is not a rounding error in a distant cluster. It is the reason there is anything here at all. There is a fingerprint left over from that moment too, and it is one of the most useful things in cosmology. When the gas was finally released, it stopped mid-wave. Those frozen sound waves left a preferred separation scale imprinted in the distribution of matter, a slight excess of galaxy pairs at a particular distance of about 150 megaparsecs, still detectable today, 13 billion years later, in surveys of millions of galaxies. It is called the Baryon acoustic scale, and it is used as a standard ruler for measuring the expansion of the universe. It exists only because ordinary matter and the invisible component behaved differently in the early plasma. It is, in effect, a receipt. And when you simulate all of this, when you take the measured initial conditions from the microwave background, put in gravity, put in the two components in their measured proportions, and let a supercomputer run it forward for 13 billion years, what falls out is a web. Filaments of matter meeting at dense knots, with enormous near-empty voids between them. The Millennium simulation, in 2005, did exactly this, with just over 10 billion particles in a box 2 billion light-years across, and the structure it produced matches the structure that galaxy surveys actually see. Nobody fitted it, galaxy by galaxy. You put in the ingredients and gravity, and the cosmic web comes out. Remove the invisible component, and it does not. So the case is closed, in a certain sense. 6 independent lines of evidence, spanning the entire history of the universe, all saying the same thing. Something is producing more gravity than the visible matter can account for, and it was doing so before the first star ignited. But there is still an obvious way out, and it is the one that most people reach for the first time they hear about this. Maybe it is just ordinary matter that happens not to shine. Cold gas, dead stars, rogue planets, black holes. The universe is enormous and mostly unlit. How could we possibly know? That objection is completely reasonable. It is also, it turns out, the single most thoroughly demolished idea in modern cosmology, and the way it was demolished involves counting atoms that existed 3 minutes after the beginning of time. Part 6. Every ordinary door closed. The obvious answer deserves a proper hearing, because for a long time it was the favorite answer, including among the people doing the searching. If galaxies are surrounded by more mass than their light accounts for, perhaps that mass is simply made of things that do not produce much light. The universe is full of candidates. Brown dwarfs, objects too small to sustain fusion, glowing faintly in the infrared and invisible at any real distance. Old white dwarfs, cooled to nothing. Neutron stars, stellar black holes, rogue planets ejected from their systems. Cold clouds of gas that never formed